Good day, everyone. I hope you're all safe and healthy. Welcome to our eighth lecture, Geometric Applications of the Definite Integral, which focuses particularly on solving the area between two intersecting curves and solving the volume of a solid of revolution. At the end of this lecture, you will be able to find the area of the region bounded by two intersecting curves and find the volume of the solid generated by revolving around the axis of rotation, the area bounded by a given function. Let's begin our discussion with the area between two intersecting curves. Given two intersecting curves F and H, whose points of intersection are points AC and point BD. The area under the curve y equals f of x from x equals a to x equals b is the definite integral of the function f of x dx from a to b. Likewise, the area under the curve y equals h of x from x equals a to x equals b is the definite integral of the function h of x dx from a to b. How to find the area between two curves? We simply get the difference in the areas under these curves. So A equals the area under function f of x minus the area under the graph of the function h of x. Substituting the corresponding formula for these areas, we have area between two curves is equal to the definite integral of the function f of x dx from a to b minus the definite integral of the function h of x dx from a to b. Simplifying this, we get the general formula to finding the area between two intersecting curves, and that is area is equal to the definite integral of f of x minus h of x dx from a to b. To find the area A of the region R bounded by y equals f of x and y equals h of x, we simply draw a typical rectangular element, or other references would call it variable rectangle, whose edges are either parallel to the x-axis or y-axis. First one is known as the vertical element of area. Since the upper end of the element touches the curve y equals f of x, then we shall refer to this y equals f of x as the upper curve. On the other hand, y equals h of x is the lower curve. Now let y sub u be the ordinate of the upper end, and y sub l be the ordinate of the lower end. Then the length of this rectangular element is y sub u minus y sub l, and its width is dx. Let dA be the area of this variable element. Then dA is equal to the product of the measures of the length and width. In this case, the measure of the length is y sub u minus y sub l, or the upper y ordinate minus the lower y ordinate. and width is equal to dx. By the definite integral, the total area bounded by the curves is given by a equals the definite integral of y sub u minus y sub l dx from a to b. This is our general formula if we are to use the vertical element of the area in finding the area between two intersecting curves. The second one is the horizontal element of area. It's horizontal since it's parallel to the x-axis. Its base or its bases are parallel to the x-axis. Since the left end of the element touches the curve y equals h of x, we shall refer to y equals h of x as the left curve. On the other hand, y equals f of x is the right curve. Let x sub r be the ordinate of the right end, and x sub l be the ordinate of the left end. Then the length of the rectangular element is x sub r minus x sub l, and its width is dy. By the definite integral, the total area bounded by the curves is given by a is equal to the definite integral of x sub r minus x sub l dy from c to d. So this is our general formula if we apply horizontal element of area in finding the area between two intersecting curves. Let's try this first example. Find the area bounded by y equals 3x and y equals x squared. We'll apply first the vertical element of area. We need to graph the functions on the Cartesian plane to visually analyze the vertical element. The red line represents the graph of function y equals 3x, and the blue curve for the function y equals x squared. Solving the two equations simultaneously, we find that the line intersects the parabola at points 0, 0 and 3, 9. Hence, since we are using the vertical element of an area, we will use this general formula. We need to determine which of these two functions is the upper y, or our y sub u, and the lower y, or our y sub l. If we draw the vertical element inside the bounded region, then the upper end touches the graph of function y equals 3x. Therefore, y equals 3x is our upper curve. On the other hand, the lower end touches the graph of y equals x squared, making it our lower curve. Therefore, area is equal to the definite integral of 3x minus x squared dx from 0 to 3. Since we are integrating with respect to the variable x, then we shall evaluate the integral from x equals 0 to x equals 3. After integrating, we get 3x squared over 2 minus x cubed over 3, and then we are to evaluate this indefinite integral from x equals 0 to x equals 3. The area between two intersecting curves is 9/2 square units. We will apply next the horizontal element of area. The line intersects the parabola at points 0, 0, and 3, 9. Since we are applying the horizontal element of area, then we shall use this general formula, which is A is equal to the definite integral of x sub r minus x sub l dy from C to D. We need to determine which of these functions is the right curve for our x sub r, and the left curve, which is our x sub l. If we draw the horizontal element inside the bounded region, the right end touches the graph of function y equals x squared. Therefore, y equals x squared is our right curve. On the other hand, the left end touches the graph of y equals 3x, making it our left curve. Since the formula is asking for x values, then we need to express our functions in x in terms of y. So, y equals 3x becomes, or y equals x squared becomes x equals square root of y. And y equals 3x becomes x equals y third. Therefore, area is equal to the definite integral of y raised to 1/2, or its square root of y, minus y third dy from 0 to 9. Since we are integrating with respect to the variable y, then we shall evaluate the integral from y equals 0 to y equals 9. After integrating the integrand, we get 2y raised to the power of 3/2 over third minus y squared over 6. And we are to evaluate this indefinite integral from 0 to 9. The area between two intersecting curves is 9/2 square units. So see, whether we use horizontal or vertical element, the answer is the same. Let's try this second example. Find the area bounded by y squared equals x and y squared equals 2 minus x. We'll apply the horizontal element of area. We need to graph the functions on the Cartesian plane to visually analyze the horizontal element. The red curve represents the graph of function y squared equals x, and the blue curve for the function y squared equals 2 minus x. Solving the equation simultaneously, the curves intersect at points 1, 1 and 1, negative 1. We will use this general formula since we are applying horizontal element of the area. But before proceeding, we need to determine which of these two functions is the right curve. So we can determine our x sub r. And which is the left curve, so we can determine our x sub l. Now, if we draw the horizontal element inside the bounded region, the right end touches the graph of function y squared equals 2 minus x. Therefore, y squared equals 2 minus x is our right curve. On the other hand, the left end touches the graph of y squared equals x, thus making it our left curve. Since the formula is asking for x values, then we need to express our functions in x in terms of y. And so, y squared equals 2 minus x becomes x equals 2 minus y squared, and y squared equals x is already expressed in x in terms of y. Therefore, the area is equal to the definite integral of 2 minus y squared, which is the value of our x sub r, minus y squared, which is the value of our x sub l, dy, and we are to evaluate this from y equals -1 to +1. But due to symmetry of areas above and below x-axis, we can redefine the lower and the upper boundaries. That is, the area from y equals 0 to y equals 1 is the same with the area from y equals -1 to y equals 0. In this example, we'll use the upper y values. That is, we are going to use the lower boundary y equals 0 and the upper boundary y equals 1. So we have area is equal to 2 times the definite integral of 2 minus y squared minus y squared dy from 0 to 1. So we have a multiplier 2 since the area of this definite integral is half of the area of the region bounded by these two intersecting curves. Simplifying further, our integrand becomes 2 minus 2y squared. Now integrating with respect to y, we get a is equal to 2 times the quantity 2y minus 2y cubed over 3, and we are to evaluate these expressions inside the quantity from y equals 0 to y equals 1. Therefore, we get the area between two intersecting curves, which is equal to 8/3 square units. To wrap up the first topic, there are two methods that we can use to solve the area between two intersecting curves. First, with the use of vertical element of the area. Second, the use of horizontal element of the area. Now, it is very important to determine which of the functions is the upper curve and the lower curve, or which is the right curve and the left curve. Also, it's very important to carefully evaluate the integral at the correct boundaries or limits. We shall now proceed to the second objective of this lecture, solving the volume generated by revolving around the axis of rotation, the area bounded by a given function. If a plane area is rotated about a line L in its plane, the solid mass generated is called a solid of revolution. And the line about which the area is rotated is called an axis of rotation. We have this area, then we revolve it about the axis of rotation, which is line L, and we generated a solid, which is called a solid of revolution. Now, if the rectangle is revolved about the line L, the solid of revolution generated by revolving it about L is a circular disk. If the lower end of the rectangle does not rest on the line L, or does not touch its base, do not touch on line L, the solid of revolution generated by revolving it about L is a circular ring or washer. If the rectangle has its edges parallel to the line L, then the solid of revolution generated by revolving it about L is a cylindrical shell. What we have on the right is an example of a cylindrical shell. Now, the volume of a solid of revolution can be found by integration. There are many methods in solving the volume generated by revolving around uh, the axis of rotation, the area bounded by a given function. So I'll discuss the basic methods. First, the circular disk. Next, the washer. And third, the cylindrical shell. Now let's begin with the circular disk method. Consider the area A under the curve C of a certain function f, and between the lines h equals a and h equals b. Assume that f is continuous on the closed interval ab. If the area is revolved about the horizontal line h, a solid of revolution is generated. Now our goal is to estimate the volume of this solid of revolution. Now how are we going to calculate the volume represented by V of this solid of revolution? So let's divide the closed interval AB into n equal subintervals. N here refers to the number of equal subintervals. Each length is delta H. Then draw n rectangles with the lower bases resting on the line H and the corresponding upper bases touching the curve C. If the area is revolved about H, each rectangular element will sweep out a cylindrical element or circular disk. Each disk has length delta H and a radius L sub I. Now the length of each rectangle is a variable L sub I, since its length changes across the closed interval A to B. And the width of each rectangle is a variable delta H, since its width changes depending on the number of rectangles to be drawn inside the bounded region. The sum of the volumes of the disks will approximate the volume of the solid of revolution. From plane geometry, we learn that the volume of a cylinder is equal to the product of the measures of its base and height. Since the base of the cylinder is a circle, then the area of the base is pi r squared. So to find the volume of a cylinder, use the formula V is equal to pi r squared times height, where this r refers to the radius of the cylinder, and at the same time, this radius of the cylinder is the length of the rectangular element, which is L sub I. The volume of the solid of revolution is the sum of the volume of individual disks whose radius is equal to the length L sub I of each rectangular element and whose width is equal to delta H. This sum of volumes can be written in sigma notation. We have V is, or the volume is equal to the sum of pi times L sub I squared times delta H, where I starts from 1 to n. Now, the limit of this sum of volumes of the disks as we increase our n, which is the number of disks, is equal to pi times the definite integral of L squared dh from A to B. Take note, this is our general formula for finding the volume of a solid of revolution by the disk method. Now let's have this example to illustrate the general formula. Find the volume of the solid generated by revolving about the x-axis, the area bounded by y equals square root of x equals 4, and the x-axis. First, we need to sketch the graph of y equals square root of x and x equals 4. The line intersects the curves at point 42. Draw the rectangular element. Note that the length of the rectangle corresponds to its y ordinate, and so L equals y. And its width, dh, corresponds to its lower and upper x ordinates, and so dh is equal to dx. If we revolve this bounded area about the x-axis, we can generate n circular disks. Each circular disk has radius y and height dx. Now, using the general formula where L equals y and dh equals dx, we have volume is equal to pi times the definite integral of y squared dx from x equals 0 to x equals 4. Since we are integrating with respect to the variable x, then we need to express the function y equals square root of x to x in terms of y. And so x equals y squared. So we have volume is equal to pi times the definite integral of x dx from 0 to 4. Integrating this, we get x squared over 2. And we are to evaluate this integral from 0 to 4. Doing the evaluation, we arrive to the answer. The volume is equal to 8 pi, or approximately equal to 25 cubic units. Let's have example number 2. Find the volume of the solid generated by revolving about the line x equals 2, the area bounded by y equals x squared, x equals 2, and y equals 0. First, we need to sketch the graph of y equals x squared and x equals 2. The line intersects the curve at point 24. Draw the rectangular element. Note that the length of the rectangle is 2 minus x because the distance of the right end to the y-axis is 2 units and the distance of the left end to the y-axis is x. Its width, dh, corresponds to its lower and upper y ordinates, and so dh is equal to dy. If we revolve this bounded area about the line x equals 2, we can generate n circular disks. Each circular disk has radius 2 minus x and height dy. Using the general formula where L is equal to 2 minus x and dH is equal to dy, we have volume is equal to pi times the definite integral of 2 minus x square, or the quantity 2 minus x square dy from 0 to 4. Since we are integrating with respect to the variable y, then we need to replace the variable x in the integrand. To do that, we will use the function y equals x squared. If we express this function in x in terms of y, we get x equals square root of y. And so we have pi times the definite integral of the quantity 2 minus the square root of y squared dy from 0 to 4. Integrating this and then evaluating the result from y equals 0 to y equals 4, we get the volume which is equal to 8 pi thirds, or approximately 8.4 cubic units.